Hello and welcome to another video. In this video we're going to be working on sum of subarray minimums. And I think this is actually a really good problem and definitely not a medium problem, so it's definitely going to be a hard problem. And if you read it, you might think it's pretty easy, but there's actually a lot here. So in the problem, you're given an array of integers and you want to find the sum min b, where b ranges over every contiguous subarray. Since the answer may be large, determine it modulo 10 9 plus 7. And the reason that it is a hard problem is because of this constraint. So this constraint allowed an n squared solution. That would be like a medium problem. But because it doesn't, because you need a linear time, it's definitely not super straightforward. So here's kind of like example 1. They show you all the possible subarrays. So this is every single subarray that's in this array. And you basically take the medium, or the min of each one, and you add them together. So here it is. So 3, 1, 2, 4, 1, 2, or 1, 1, 2, 1, 1, 1. Add them together in 17. This one's kind of a lot, so a lot of numbers. And the reason that it's difficult is because to do subarrays in linear time, you kind of have to break it down into some kind of way where ideally you want to figure out some criteria for all subarrays that do something. And then that's something that you pick, you should be able to calculate in O of 1. So for example, something really common is like all subarrays that end with index I, right? So for example, here, it'd be like, let's just take all subarrays that end with 3, all subarrays that take with 1, all subarrays that end with 2, all subarrays that end with 4. And each one of those you have to be able to do in linear time, or non-linear, in constant time, usually by some kind of pre-computation, like a prefix sum or some kind of other trick. But here, the tricky part is you need to figure out actually all subarrays that instead of end or start with an index, what you really need is you need all subarrays that have index as min element. So, for example, here you would say like, okay, give me all subarrays with 3 as the min element. Well, that's just 3. And you need to get that in constant time. Then all subarrays with 1 as the min element, so that's going to be this one, this one, this one, this one, and this one, and this one. Then all subarrays with 2 as the min element, which is going to be this one, this one, this one, this one, this one. Not this one. So let me go back. So it's going to be just not that one either. So it's actually just going to be these 2. And then all subarrays with 4 as the min element, which is 4. And it's very tricky to do this in constant time. So if you are able to do this in constant time, then you can go through every index, and through every index you can get an answer, right? So if you know like how many subarrays are there for each number, you can just take that number of subarrays, multiply it by the number, and that's your answer. But it's very tricky to do this, and I don't think it's very intuitive, and it's a pretty rare problem. So let's kind of walk through how we would do it. And I wasn't able to actually solve this on my own, so I had to look at some solutions and look through the editorial, and then it made a lot of sense. But the nice thing is now that I have seen it before, I will be able to do this kind of problem, or the reverse, where you want to get the max. So here is a sample subarray, or just an array. And this is the one that they actually used on an editorial, and it's a really good example on how to do things. So basically our goal is to, for every single number, figure out like where are all the subarrays that start and end with that number. So for this, for example. Now the first part to this problem is what we really want is given, let's say we know like for 8, let's say we know for 8, what's the like constraints of how many numbers to the left and how many numbers to the right can it have such that this is 8, right? So for 8, you can't really have anything to the left or to the right, right? That the minimum is an 8, because if you start including like a 6, then the minimum won't be 8, it'll be 6. So for 8, there are 0 numbers to the left and 0 numbers to the right. And so the number of combinations of subarrays with 8 is just 1, just this 8. Now let's go through another one, and then this will make more sense. So instead of 8, let's pick, we don't want something too big, so let's pick, let's see here. I guess we could pick 6. Or actually, we can pick something a little bit bigger. Let's go with 4. 4 is a good one. So let's say 4 is our smallest element. How many numbers are there to the left of 4 that we can actually include, and how many are there to the right? So 4, there's actually only 1, right? So it's this one over here. and this one over here for the right. So there's one to the left, one to the right. But also, we need to include the subarray where it's just 4. We also need to make sure we include the subarray where it's like 5, 4, right? So we need to include subarrays where there's nothing to the right, and we need to include subarrays where there's nothing to the left. So actually, the way we're going to represent this, instead of saying there's only one number, right? Like these are the bounds for 4. We can't go anywhere past this, because anywhere past this, it would be too far, right? So there's one thing to the left, one thing to the right. But we do need to include like some of these not existing. So actually, instead of 1 to the left and 1 to the right, we're actually going to write 2, because the second one will just be the empty array. So there's actually 2 and 2. And that means that there are, so if you know that there's 2 combinations to the left, 2 combinations to the right, you just multiply those and you have 4 arrays. And let's actually write them out here. So one combination is 5, 4, right? One combination is 4, 9. So let's actually take all these subarrays. Let's start in order. So let's take all the subarrays that include this 5, but there's an empty subarray here. So that's just going to be 5, 4. Now let's include the subarray where these are both empty. So that's just 4. Now let's include the subarray where they're both there. So 5, 4, 9. And let's include the subarray where this left thing is empty. So that's 4, 9. So you can see for an array, we can make this general statement. So for an array, or for an index, I guess, or for a number, the number of subarrays with that index is number of elements to the left that we can include plus 1 times number of elements to the right that we can include. And this works, and this is plus 1 as well. And this works for any subarray. So we can now quickly do this for any subarray we wanted. Like let's say instead of this, we wanted to figure out how many subarrays are there with this 3. So how many elements to the left we can include. Remember, it's every element that's right next to it that is bigger than it. So it's just going to be these 2. And then to the right, it's going to be all of these. So for 3, the number of subarrays, this is 2, this is 3. Remember, we add 1 to each of these to include the empty array. So plus 1 and plus 1. And here we get 3 times 4, which is 12. And so now that we know that, we can actually really quickly, before we go on, go back to example 1 and calculate this just like really quickly. And then we can kind of figure out how we can do this in OVN. So let's go back to this example. So for 3, we can do this really quickly. So there's nothing to the left, nothing to the right. So 3 will just have 1. It'll have a left of 1 and a right of 1. Right? So that's just 1. Let's actually just write it in here. So 1. And remember, it's how many arrays times that min element, which is going to be 3. Then for 2, or for 1, 1 can go all the way. So number of elements to the left is 1. Number of elements to the right is 2. Remember, we add 1 to each of those. So it's going to be 2 and 3. So 2 times 3 times 1 plus 2. How many elements are there to the left? 2. Actually, no. To the left, there's none, because we can't include this 1, because if we include this 1, then 2 is no longer the min element. So for 2 to the left is 0, and to the right is 1. Remember, we add 1 to each, so it's going to be, if it's 0 and 1, it's going to be 1 and 2. So 1 times 2 times the value 2. And then for 4, there are no elements to the left, because all of these are smaller, and no elements to the right. So it's 0, 0, which will just be, you add 1 to each, so 1 times the value 4. If we add all these together, we get 3 plus 6 plus 4 plus 4. Which should ideally be 17, and it is. So that's kind of like, now you know kind of how to do it, right? You can figure out how many subarrays are, like how many numbers can we include for a given minimum. And now that we can do that, we can actually calculate this. But we have to be able to do this in O of 1. So we can't just like go to a number and then just like search how many elements can we include. And then go to this number and search how many elements can we include. So the way to figure out for a number, what we really need is the constraint, right? Like what's the, like for a given number, we need to really figure out like where's the location of the element that is smaller than it on the left and the element that is smaller than it on the right. And the way to be able to do this is actually a monotonic increasing stack. So a way a monotonic increasing stack is every element on your stack will be strictly increasing. So you have like 1, 5, 3, 9, and so on. And the way this will work is we can quickly describe this. So let's say we put 8 on the stack. Then we try to put 6 on the stack, but we have to have it increasing. So because it's not, we can't put it on the stack. We have to get rid of 8. So once we get rid of 8, we can figure out its left index of like the element that is less than 8, right, by the thing on the left of the stack, because it should be increasing. So if there is something here like 6, it's going to be the index of this number. Because the stack is empty, the index of the element that is less than 8, there's nothing, right? 8 is, so everything from 8 to the left, it can be included. And the right is just going to be everything before 6, right? Because we're putting on 6. 6 is smaller, so that's going to be the index. Then we put 6 on the stack. Let's actually write it over here, right? So let's just walk through like all of this and write it over here. So we put 8 on the stack, and we're going to put it on with its index. So we're going to put 8 and 0. We're going to put on a tuple. Then for 6, we're going to say, okay, well, 6 is smaller than 8. So we need to pop off 8 because we need a strictly increasing stack. So we pop off 8, and we have 8 and 0, right? And then because there is no stack, that means there's nothing to the left of 8. So the number of elements is 0 plus 1, right? So it's just going to be 1. And then the number of elements to the right is whatever the index of 6 is. It has to be everything before that. So if this is 0, this is 1, there are no elements there either, right? Because there's nothing in between. Like we have these two indices. So the to the right is also 0 plus 1. So it's going to be 1 times 8. And then we add that to our result. So our result will be 8. Then we put 6 on the stack. So let's get rid of all this. And let's kind of show where we're at as well to maintain this. So we put 6 on the stack with its index, so 1, 6. Then we move to the next element. Then for 3, we kind of do the same thing. We say 3 is less than 6, so we'll just pop off 6. And using these indices, we know that there's nothing to the left of 6, right? So to the left of 6 is this whole thing because there's nothing on the stack. So that's 2 elements, or actually to the left is only 1 element, so 1 element to the left, and no elements to the right because 3 is right after it. So if there's 1 to the left and none to the right, remember we add 1 to each, so it'll be 2 times 1 times 6, which will be 12. So we add 12 here, get 20 as our current total. Then we add this onto our stack, so this is 2, 3, and then we move on over here. So for 5 is greater than 3, so we can just add that onto the stack. And let's get rid of this arrow, actually. So yeah, for 5, we can just add it on directly. So we'll add it and its index, so 35. 4 is less than 5, so we have to pop off the 5. So we're going to pop off 35. We're going to check the left side. Is there something on the stack? Yes, there is. There's this 3 element. So the element that is smaller than 5, the one to the left of it is 3 at location 2. So this is the distance that we can go, right? So there's if we have a 5, this is basically no distance, right? Because this is index 3, this is index 2. So there's nothing to the left. So left is 0. And right is also 0, right? Because 4 is right after it. So 0, 0, add 1 to each. So 1 times the value 5. We get 5 here. So now this is 25. So we can update this. Get rid of that. Get rid of this. And now we put on this 4. So 4, 4. Then we go to the next one, 9. 9 we can put straight on the stack because it's increasing. Remember, we're sorting by this element on the right, right? The left index is the index, or the left number is the index, and the right number is the value. So we can write that as well up here. So it's going to be index value. Okay, so now we can put this on directly. So this is just going to be index 5, value 9. Now here, we're going to pop as much as we can until we can put it on the stack. So we have to pop this 5, 9. So we have to figure out what's the left of it. So to the left of it is 4, index 4. So there's no elements to the left, right? Because it's 4 and then 5, so there's nothing in between those. So left is 0, and right is this index here. So right is also 0. Add 1 to each. So you get 1 times 9, which is 9. So 25 plus 9, 34. Okay. Now we have to keep popping because we're trying to put on 2, and 2 is still smaller than these. So we pop 4, 4. And what's to the left of 4? So to the left of 4 is this number here. what's the distance between those? So this is index 2, 4 is at index 4, so there's 1 in between those, right? And that is true. So with 4 as the min element, this is the element that's to the left, so there's 1 element to the left. And how many elements are there to the right? So the element to the right of 4 that is smaller is this one over here, the one we're currently on. So there's also 1 element here. So left is 1, right is 1, which means we add 1 to both. So we have 2 times 2 times 4, which is 16. So plus 16, you get 50. And that makes sense, right? Because with an array with a minimum of 4, these are like the valid numbers we can use. Anything past that, the minimum is not going to be 4. So we get rid of that. Now we still have to use this. We still have to get rid of that because the minimum element is 3 and 2 is smaller, and we need an increasing stack. So we're going to pop off 3 as well. So 2, 3. Now there's nothing left on the stack. That means the minimum element, or the left element of 3 is nothing. Like there's nothing on here. So that means we can go all the way here, which we can. And to the right, it's going to be every element before 6. So how many elements is that? There's 3 over here and 2 over here. So 3 times 2, and you add 1 to each of them, so it's going to be 4 times 3. So 4 times 3 times 3, which is 9 times 4, so 36. And we have 86. Get rid of all this. Oops. And now finally, we put on 2 with index 6, so 6, 2. Now at the end, you might have, like right now I have 1 value, but you might have a bunch. So whatever you have at the end, you basically have to pop off 1 at a time. And you know that, like let's say I had more values, just to quickly show this. Let's just say I had 1 more. So let's say this was at index 9 and this was value like 5. That means that when I pop this value, there is nothing to the right of it, right? Because this is the top of the stack. That means this is the smallest, like there's nothing smaller than it to the right. So whatever, if this was at index 9 and the array was length 15 or something, like the whole rest of the array from index 9 would be valid, and then the thing to the left of it would be this value. So the thing to the right is whatever's above, and the thing to the left is whatever's below. So once you start popping off from the end, there's nothing to the right. Okay, because it's an increasing stack, right? So if our numbers are like 1, 3, 5, 7, and so on, there's nothing smaller than 7 to the right of 7. There's nothing smaller than 5 to the right of 5. There's nothing smaller than 3 to the right of 3, and so on. So now we pop off this value, and we basically pop all values until our stack is empty. So we pop off 6, 2. So remember, the thing to the right of 6, 2 is just the whole rest of the array. Unfortunately, there's not anything here. So this is 0. And the thing to the left, there's nothing to the left. So it's this whole array here. So this is 6, and right is 0. So add 1 to each. So 7, 1, and 2. And we add another 14, and we get 100. And so that's our answer. And there's one more tricky thing, like this is basically it. And there's one more tricky thing that I want to go over, which is duplicates. So if you have duplicates, I'm not going to show the stack again, but I'll kind of just show what we want to be doing. And that's why we want to have a strictly increasing stack. So let's say instead of this, we have some numbers here. So let's say that we have a 2 here, and we have a 2 here. Basically what's going to happen is like for each 2, we will consider it separately. So for this 2, our range will be this range. Then for this 2, our range will be this range, right? We don't want to count the same thing twice. So like for this 2, we don't want to use this range. And for this 2, we don't want to, because then we have overlap, like we're reusing things. So you can't use multiple 2s in one thing. But what you can do is you can get rid of them. That's why you have this strictly increasing stack, so that for the left one, the range will only be up to here. But then for this one, the range can be the whole thing. And then the right one, and that makes sense, right? Because like this is a valid array, but we want to only count this for one of the 2s, not both. So the way it's going to work is for an array with these 2 2s, we will only count as this 2 being the min element. And for this 2 being the min element, we will count everything up to it. And for this one, for this array, we will only count that with this being as the min element. That's why we have a strictly increasing stack, and it'll work for that. If you had equal or something, then you would have duplicates, because like for this array, you would count this, and then for this array, you would also count this, and that would be duplicates. So that's basically it. So let's take a look at the code. And like I said, I have no idea how this is a medium problem. I don't think it is. But also one small mention is now that you know how to do this, you can also do the same thing if you had the max. So instead of if you had the max, instead of having an increasing stack, you would have a decreasing stack. So let's say I had some numbers, I would just put like 8 and then 2, and then I would have a 3. And then when I put the 3, I need my stack to be strictly decreasing. So what would happen is I would pop off this 2, and then I would know, okay, the thing that's bigger than 2 to the left of 2 is over here, and the thing that's bigger than 2 to the right of 2 is the thing that I'm just putting on. So you can basically just reverse the type of stack you have to have the max element. So this will work for min or max. But like I said, I think this is a very rare problem, and all stack problems are also very rare. Well, not very rare, but this one's very tough, I think, to figure out like all the combinations. So I think once you do see it, it's definitely going to like help you do similar problems. And this is a very rare type of problem compared to other problems, right? Like DP you see like a billion times. So, okay. So let's take a look at the code. So what I actually did was I wrote some code that was a little bit messy. And then what you can do is you can basically just put it into ChatGPT and you can say like, my code's a little bit messy, give me better variable names and add comments. And it will do something like this. So my code was this, but the variable names were bad and the comments weren't there. So this will, like, that is what it's good for. If you do have a working solution, it can make it cleaner. But if you don't have a working solution, a lot of the solutions it comes up with are pretty bad. So get a working solution. And then if you want it to just like write something with better descriptive names, comments, things like that, you can ask it to do that. Okay. So here we have the mod, because we need to, like, the number can get big. So we just have a mod, we have a stack, we have a total sum, and we have the length of the array. Then essentially we are looping through our elements. And every time we encounter a number that is, so in this case, that is smaller or equal to than the top of our stack, we will pop off the top of our stack. We will figure out the left count for it. And the left count, remember, is going to be the item on the stack that is before it. So let's say we pop off an element here. The left element will be the thing before it, or if the stack is empty, then you can use the whole array. And then the right element will be the thing that you are pushing onto the stack right now. So you get the left, you get the right, you increase them both by 1, and then your sum is just left times right times the value popped. And you just keep modding it by mod. Then finally, when you do have a stack left over, remember you will definitely have a stack left over, because you're not going to pop off the whole thing. You're always going to push on the last item at least. But you might have a lot of elements. You just keep popping off the stack. The right will now be the whole rest of the array, because you will have a strictly increasing stack. So the right will always be the whole rest of the array. And then the left will either be the previous element, or if the stack is empty, it'll be the whole left of the array. So you get the right, the left. Remember, add 1 to both of those to account for the empty array. And then the total sum, you're just going to be adding the left times the right times the value. So very similar to this code. Modded by mod and return, and we can submit it. And yeah, I have no idea how this is a medium problem. Like, no way. So like, there's hard problems that I could do in 5 minutes, and this one is tough, I think. Or just maybe I haven't seen enough of it. I don't know. Let me know what you guys think about it. Definitely not super intuitive for sure. Yeah, so this is pretty efficient. So now basically we got our runtime. And like I said, the thing that makes it hard is because you need a O of n or n log n runtime. So now with a stack, like usually stack problems, you basically put items onto the stack once and then you pop them off once. So your runtime will be O of n. So here the time is O of n, because you're putting an item onto the stack once, popping it once, space O of n for the actual stack. And yeah, I definitely think this is a really good problem. I did also see like the acceptance rate's really low, and the problem is for most problems that have given solutions, usually the acceptance rates are like super high because people just copy paste solutions. So even with something that has like a solution in a tutorial, if the acceptance rate is low, that means it's a tough problem. And I was reading like the comments, and pretty much everyone said like, I don't know how this is a medium problem. So yeah, let me know what you guys think about this. Let me know if this was helpful, and if you did like the video, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.